that I was just showing you a solution that looked like what I would do if I didn't know how to do any kind of vector addition. And now I want to show you what I would do using some vector addition. So there's Jane and Bob, and I don't know, I kind of want to make a statement about whose way is simpler, but there's something easy about Jane's plan and there's something easy about Bob's plan. So Jane is trying to start here and go straight across. And in order to do that, she has to aim upstream because the river is going to be pushing her downstream. And if she just aims for the finish line, she's going to get carried this way. And that's what Bob's doing. So anyway, I want to figure out how long it's going to take Jane to cross. And I'm going to be finding some other stuff too. So let me write Jane. And you don't have to copy any of this. This will be here for you if you want. I'm using an extra sheet of paper. I don't know if you even have paper. And I'm going to divide my paper up into two things. There's sort of the vector addition part, and over here is the kinematics part. And I'm going to be writing some stuff and then crossing it out just to make a point. So first, the vector addition part, I think I'll draw a picture first. And I could start with the table first, but I'm going to start with the picture. This is what Jane's trying to do. Jane is going to go this way, but not really. This is Jane's speed and heading. I'm just going to abbreviate that S and H. And that represents her speed and heading. And then the river's velocity is like this, which I'll just abbreviate RV for river velocity. So this is actually Jane's path. This is, I'm going to call it JV for Jane's velocity. So if you were to watch this on some tracking mapping program, you would see Jane go straight across the river. You wouldn't see this, you wouldn't see that. But they would be this vector and this vector, they'd be added together to give you that one. So in terms of putting this into some kind of a table so I can neatly understand what's going on here, here's X and Y. And even though probably it would make sense to call this north and this south, I just want to say Y instead of the north-south axis. And I just want to say X instead of the east-west axis because that's just easier. So there are three different vectors. Which one's the resultant vector? Just blurt it out if you know. Jane's velocity. It's the velocity of the star of the problem, the object that we're focusing on. It's actually how fast it moves across the earth in which direction. So I'm going to put down here JV and over on the left just to keep track of things. That's the resultant. And then the other two vectors that should add up to that are the speed and heading. And that's a component. And then the other one is the river velocity. So that's a component. So these two vectors have to add to that one. This is a weird problem. Normally I don't give problems like this. So this is actually a tricky problem beyond a regular river problem. We know some things. We know the river velocity. Does anybody remember? 2. Now, if I want to put that in here, where's the 2 go? The X or the Y?
0, -2.
Yeah, so 0, the river's not moving left to right here, but it's going down my paper at 2 meters per second. I'm leaving units off, but it's meters per second. Speed and heading here. Do I know like the X and Y values of that? This is where it gets kind of weird. Nobody's said it yet. So the quick answer is no. So Jane's velocity. Do I know the X or Y components of Jane's velocity?
80.
What's that? 8. So 80 is the distance across here. So this X and Y, these are I'm doing velocity right now. So these are velocity vectors. So the one we know for sure absolutely is what? X or Y? We know the Y. What's our Y velocity? The Y component of that is 0. Okay. So this is actually maybe a little complicated to figure out. And let's see. Speed and heading. We know her speed in still water is 3, but that means this is 3. We don't know the x or y components of that. So there's one other thing I can fill out in this chart without really doing any special math. What is it?
Or y.
Her,
The
speed and heading's y. What's that?
2.
It's got to be positive 2. So this speed and heading right here, it's at some funny angle, but the next thing I'm going to do is I'm going to resolve that into the x and y components and draw a little picture of it. But this component vector and this component vector add up to the resultant. So in the x dimension, they should add up, and in the y dimension, they add up. And if the sum is 0 and this is negative 2, then that's got to be positive 2. So I want to fill out some other stuff, and to do that, I'm going to take this and draw it down here and do some stuff with it. And it's going to look a lot like this diagram, but a little bit different. So this is her speed and heading. And I want to get the x and y components, or at least I want to have a diagram showing the x and y components. So this, let's see. So there's the x component of this. This is the x, I'll write S and H sub x. And then here, this is S and H sub y. And this one we know, this is 2 meters per second. And we actually do know this. How fast can she paddle in still water? 3 meters per, so that was given in the problem. They can paddle 3 meters per second. So this is 3 meters per second. So we can get this now. So what's this? If this is 2 and this is 3? Yeah. So this is 9. Oh, well. 3 squared is 9 minus 2 squared, which is 4. So we get 5, and then the square root of that would be square root of 5, whatever that is. So this is the x component of the speed and heading. And this is the y component of the speed and heading. And when you put them together, you get that 3. So just for the heck of it, I can fill out the rest. What's the x component of her actual velocity going across the river? Yeah, whatever that is. So now I can do some kinematic stuff. And I told you this is going to seem like a lot, but hopefully it's all kind of sensible. And even if you don't do it, you can see how it all fits together. All right, this is a jump. I've never done this before with you. I'm going to write some stuff, and then I'm going to cross some stuff out. So this is the x dimension. This is the y dimension. And this is, we can do this because of that big idea that in two-dimensional motion you can analyze what happens in the x dimension and the y dimension separately. And neither one really affects the other. So they're tied to one another, as you'll see in just a second. So I'm going to list a bunch of stuff and then cross a bunch of stuff out. Remember, there's V0, there's V, there's average velocity, there's change in velocity, there's acceleration, there's time, and there's displacement. So I could do that in the x dimension, and I could write all this stuff. We can have different kinds of velocities and accelerations and whatnot in the y dimension, and I could just do kinematics problems on what's happening left to right, and then I could do kinematics problems on what's happening top to bottom. So I can cross out a bunch of these. In the x dimension, which of these can I cross out? Or it might even be better to say, which of these can I not cross out? But let's do which ones can I cross out? Which ones don't exist? Maybe. Okay, I'll cross out V0. What else can I cross out? Acceleration. More. Change in velocity. More. So, well, here it gets kind of iffy. So V0, V, and average velocity, they're all the same. If you don't have any acceleration, then there's no change in velocity. If there's no change in velocity, then v0 and v are the same. And if v0 and v are the same, then the average velocity is the same. So I really only need one of these things. I'm just going to call it vx, the x velocity. And really, I could just call it rate. What I've got left is rate, time, and distance. So since there's no acceleration, the whole thing is simple. You can just use distance equals rate times time to solve problems in the x dimension. So let's go ahead and see what we can solve. So just in the x dimension, do I know any of these three things about Jane's trip? Yeah, so delta x is 80 meters. That's how far she's going across the river. It doesn't matter whether you're looking at this path or you look at that path. In the x dimension, it's delta x is 80. Okay, what else do I know? Do I know the time or do I know the x velocity? The x velocity, if I look at x here, x velocity of this is square root of 5. X velocity of that, square root of 5. So no matter what, her x velocity is that. So how do I get the time? Plug it into the equation. Distance equals rate times time. Or I could write, average velocity. I'm going to write this since I crossed out average velocity equals displacement over time. So the velocity is root 5. And delta x is 80 meters. And then I have delta t. So solving for this is just going to be, it's going to ultimately be 80 divided by the square root of 5, which I think is 26. No. What is it? 20. What is it? I'm going to use my forbidden calculator. When I was thinking of this last night, somebody asked me to show them how to do something on the phone. And I felt like somebody said, can you teach me how to use the dark side of the force? Anyway, so 80 divided by 5 square root, 35.7, 35.8. What? What's going on? Oh, you're hearing a ringing sound? I'm sorry. I can't stop it. We could try to cover it up. Does it do it all the time, or is it just today? Huh. Yeah. Boy, now you've ruined it for everybody else. So we're done, really, with this. But for the heck of it, let's do the y dimension stuff. So what can I cross out over here? In the y dimension, which of these things don't exist? Everything that doesn't exist, well, maybe everything that doesn't exist over there for sure. So I'm just going to leave Vy and get rid of, because there's no acceleration in the y dimension either. This is going to be,
no change in x either, right?
And,
Let's change in y.
Right, yeah. So, but I'm going to leave these because it's possible that they do exist, but we'll see that they don't. Now, one of these I've already got. One of these is the same as this dimension. What's that? Time. Time is the same in both dimensions. So, yeah, that'd be weird if it weren't. Somehow time left to right is different than time up and down. I'm glad that's not the case. That would make physics hard. So instead of delta x, I should have delta y. So if we look at the resultant, delta y is 0. And if we did the math here, if delta y is 0, then average y velocity is going to be 0 too. So it wasn't very interesting, but you can see we could have done stuff there. All right, so that's it for Jane. Jane takes 35.8 seconds to get across the river. Now Bob. What? Yeah, I'm pretty sure that's right. So with Bob, here's the vector part. And here's the kinematics part. And with Bob, this is kind of an extended problem because Bob does one thing and then Bob does another thing and there are two intervals, and I'll get to that in a second. So drawing a picture, here's what Bob does. He aims over here, and then he gets carried down the river by the current. So it's like, whoop, that's not right. No, that is right. So this is his, this is his speed and heading right here. And this is the current, and this is his actual path. So this is the Bob velocity. This is the river's velocity. This is Bob's speed and heading. And we know speed and heading, we know the value of that's 3, and we know the value of this is 2. So this is kind of an easier vector problem because we know the two components, and we're just adding them up to get that. So that's the easier kind of problem, but I'll write it out anyway. Here's x, y. So we add these two components to get the resultant. This is the speed and heading. This is the river's velocity, and they add up to give us Bob's actual path and speed. So the speed and heading, what are the x and y components of that? Like, is it 2 and 6 or 7 and 5? This vector, 3 and 0. And what are the x and y components of the river's velocity? 0, negative 2. So when I add them up to get Bob's actual velocity, it's just going to be 3, negative 2. And I could, if I wanted to, if this was one of those kinds of problems at this point, we could figure out what the angle is. We could do what you've been doing in other problems. But I don't think we really need to do that. I'm going to jump to the kinematics. So here's the x dimension. Here's the y dimension. And this is for the river crossing. There's another part to Bob's story, which is where Bob runs up the bank, runs pretty fast. Just to show you I'm just going to use, I kind of just want to use distance, rate, and time. I'm going to do that. So distance is really, it's like delta x. And rate, this is like x velocity. And time is just time. Doesn't matter which dimension we're in. And in the y dimension, we also have distance, rate, and time. This is the way river problems are because there's no acceleration, so they're simple. When we get to projectile problems, in which of these dimensions will we have acceleration, x or y? Y. So the x dimension can still look like this, but the y dimension is going to have all those other things. All right. So I'm just looking at Bob's x stuff. So we're thinking about his, like, this is the x dimension here. Do we know the distance? The x displacement? Yeah. Is what? 80 meters. Do we know Bob's x velocity? Like the x component of his velocity?
I think the last time was just...
What's the x component of velocity? 3. So we can figure out the time. So it's just going to be 80 divided by 3, which I don't remember what that is. 80 divided by 3. 26 I should have remembered that. 26.7 seconds. So what can I do with that? Because what's happening in the y dimension and the x dimension, they're happening at the same time. So the time interval is the same. Now, do we know the y distance right here? Do we know this distance? No. Do we know the y velocity? What's his y velocity? Negative 2. So that's the rate, negative 2 meters per second. So if I'm using distance equals rate times time, I can find the distance by multiplying the rate times 26.7, and I think it's 53 something, times 2 equals 53.3. Oh well, negative 53.3 meters. What does the negative mean here?
He's going up.
He's going downriver. So I'm not going to do this formally with the next part, but if I wanted to continue with this, actually for the heck of it, I'm going to do it. So this is the so-called bank run. This is not when people run on the bank, like demand their money out of the bank. This is when Bob runs back up the bank. So I'm going to do X dimension, Y dimension, and I'll do distance, rate, time, distance, rate, time, and in my picture over here, here's what he's doing. He's going across here, and then he's going up there. So we just dealt with this interval. This is the interval now. And some of this is going to be really silly. So in the X dimension, what's the distance he travels in the X dimension? Nope. 0.
Oh.
What's his rate in the X dimension?
8 meters? No. He's running like 8 meters per second.
Which way is he running?
Oh.
What's his rate in the X dimension?
0.
0. Time? We can't really figure it out from this. I mean, no matter, so if distance equals rate times time, and we know the distance is 0 and the rate is 0, I don't think we can really reliably solve for t there. So we have to find t a different way. T could be anything at this point. Yeah, he could be crab walking, pointing he could be looking this way, walking sideways, 4 meters, whatever. So now in the y dimension, what's the distance that he travels? How far is it from here to here? Well, right here we found out that when he did this, his y displacement was negative 53. So to get back to here, this has got to be 53.3. And what's his rate going this way? This is from the problem. Does anybody remember? How fast can he go on the bank? 4 meters per second. So now we can do it. So if distance is rate times time, 4 times t, so t is just 53.3, oh, not minus 0, divided by 4. 13.3. So just to dot my I's and cross my T's, this is also 13.3 seconds, which still works in that formula there. All right, so the total time is 13.3 seconds plus 26.7, which gives you 4.